This video is the third and final video where we will now finish the exploit for stack level 0 from Protostar, which we have compiled on a modern system. In the first part we got a general overview of what has changed when the code is compiled with a modern compiler and looked more closely at the stack cookie. In the second part we then ignored the stack cookie for now and identified a few more exploitation mitigations and developed a bypass for them. So only one thing is left: finally defeating the stack cookie. Like we talked about in the first video, we can brute force a stack cookie if the binary is a 32-bit binary. There are around 60 million possible values for a stack cookie. That's not that much, but 16 million executions is maybe a number where you start to want to optimize a bit. While I am not an expert in super fast computing, I decided I didn't want to write a potentially slow Python script, but write some C code. But like I said, I'm not an expert in what is the fastest way, and I actually suspect that maybe the bottleneck here would not be a slow script, but the kernel, which has to do a lot of stuff to execute the program over and over again. So maybe it's unnecessary to write a C code, and maybe my C code is very bad too, but I just wanted to mention it that it's not always easy to decide what is the best approach. Now that we said that, let's try to approach this step by step. First, how do you execute a program in C? Well, there is a system call for it called exec, but usually we never call syscalls ourselves directly, but use wrapper functions provided by something like libc. So libc offers a few different versions of exec, but they ultimately all use the same exec syscall underneath. It says here in the man page: the exec family of functions replace the current process image with a new process image. I think when you never thought about how a program is executed before, this sounds really weird. Why do you replace the current process and not just execute it? That's so weird. Well, that's just how it works. That's the execution model of Linux. And so in our case, we don't just want to exec and thus replace our program, but we want to execute the stack0 binary as a new process over and over again. To spawn a new process, we have to fork the process before we exec. Fork creates a new process by duplicating the calling process. This new process is referred to as the child process. The calling process is referred to as the parent process. And maybe also interesting, it's down here, difference between C library function and the actual kernel. Since version 2.33, rather than invoking the kernel's fork system call, the libc fork wrapper invokes clone with flags that provide the same effect as the traditional system call. So what you do to execute the process over and over is to first fork our current process. Now we have a child, an actual new separate process, and you have to imagine this code is now duplicated. We have two processes running the same code, just one runs as the child and one runs as the parent. You can check the return value of the fork, which process you are. In the parent process you get the PID of the child, and in the child it's just 0. And in the child process we can call exec to replace the current process with stack0. Now in our case we want to communicate with the child, meaning we want to write the exploit input to it and read the output of it to determine if we were successful. Usually you would do this by creating pipes. Pipe creates a unidirectional data channel that can be used for inter-process communication. The array pipefd is used to return two file descriptors referring to the ends of the pipe. Pipefd0 refers to the read end of the pipe, and pipefd1 refers to the write end of the pipe. Data written to the write end of the pipe is buffered by the kernel until it's read from the read end of the pipe. Basically the same pipe you can use on the command line. You pipe std out from one program, cat, into the std in of another program, grep. That's why we call this character a pipe. So for basic std in and std out communication, you would create two pipes. And then when you fork, because you clone the process, the child and the parent have access to the same pipe. Now obviously, depending on if you are the parent or the child, you use one or the other side of it. And in the case of the child, we are actually going to replace the default standard in and standard out now with those pipes by calling dub2. The dub2 system call performs the same task as dub, and the dub system call creates a copy of the file descriptor. after a successful return, the old and the new file descriptor may be used interchangeably. They refer to the same open file descriptor and thus share everything. But dub2, instead of using the lowest number unused for file descriptor as dub, it uses the descriptor number specified in newFD, the second parameter. If the descriptor newFD was previously open, it silently closes before it's being reused. So dub2 closes the current std in and std out of the child and plugs in the new pipe we created. And when we exec the stack0 and replace the current process with the new one, stuff like open file descriptors stay intact. So the new process will use the pipes we just connected to for reading input and writing output. And then in the parent, we can simply read and write to the end of the pipe and thus communicate with the child process, stack0. A nice thing to do is to close the ends of the pipes you are not using in either process. So for example, we don't need the reading side of the std_in pipe because we want to write, send data to the child process. Okay, once we have written our buffer overflow input, we can wait for the child process to finish and read the output to see if we were successful. Now here's the first big issue: buffering. libc will buffer output you write. So the output of the child process is buffered in the process, and you can imagine that if we do a buffer overflow, screw with the stack and get a seg fault, this buffer is lost. The program is just dying horribly. But maybe you think that doesn't make much sense, because we showed in part 2 that our exploit theoretically works and we see the output on the shell. We saw the modified variable message. So how does it make sense that the shell would see the output, but I'm telling you now, we won't see it with the code we have just written? Well, there's a difference to how libc buffers output depending on what kind of pipe it's connected to. And in our case, we've just used regular pipes, and libc will buffer the output data until the process calls flush, or maybe until it's filled nicely, maybe after 1024 bytes or so. I don't know. But we have neither. The output is super short and the child process never calls flush. So what's the difference on the shell? Well, programs executed by the shell are not connected via regular pipes, but are connected to a pseudoterminal, pty. And where libc sees that the output is written to a pty, pseudoterminal, then it will flush the buffer upon a new line. Because new lines are like the ultimative indication that you want to print a new line on the terminal output. I think it's like a speed thing. You don't want to flush if it's not necessary. But on the terminal, you want to see outputs after a new line. This means we could also execute stack0 program in the context of a pty, so that we fool libc into flushing on every new line. And there is a convenient libc function that does that for us, called forkpty. The forkpty function combines openpty, open a pseudoterminal, fork, which we already know, and the login_tty call to create a new process operating in a pseudoterminal. The file descriptor of the master side of the pseudoterminal is returned in a master. So that's really cool. We fork a child process and already get the file descriptor so we can communicate with the child process. Then I disabled a few options of the terminal. For example, I don't want to echo the input again. For example, if you watch my embedded hardware security CTF videos, you notice that usually whenever I type something on the shell to the board, I don't see characters I type. That's because I didn't configure the terminal to echo back the characters. While it would have been nice there, I don't need it here, and there are a few other options that could screw with what we want to do. And then we also don't have to fiddle with pipes, so the child is just exec now. In the parent, we define our buffer overflow input. That's basically the one we developed last video, and then also add some random function to get 3 random bytes for the cookie, and place those into the buffer overflow string. A simple ugly loop to avoid new lines, because that will indicate the end of our input and we don't want that. Then we write the buffer overflow string to the master file descriptor of our pseudoterminal, and stack0 will read it and will get exploited. Then I create a short loop to check the status of the child. But I don't want to block and wait for it, because the child could horribly die or not die because of the buffer overflow. So I just check the status a few times in a loop, and if the child is dead, we can continue. If we waited already a few times, we decide to kill the child process, and otherwise we sleep a bit. Usually it shouldn't loop much as the child program is very short, but it's a safety net. By the way, program IDs, PIDs, are prone to race conditions in Linux. You see, we don't have some kind of handle directly pointing to the child process, we only have a number. Numbers can be reused, so theoretically our child could have died and another process like web server could have been executed and assigned our old PID, and then we kill it here. And there is no better way in Linux, it's just really ugly sometimes. Anyway, one other thing I want to add now is a signal handler, which will be notified if the child dies or so. We could just read the output after the wait, but we don't know why and how the child might die and so forth. And I also found it to be a third slower if I do that. So use the signal handler instead. The signal function is called to notify us if anything happens to the child, so when it receives a sick child. And in the handler function, we then read from the terminal the output of stack0. First we read the try again message, and then potentially read the stack smashing detected error, or maybe the successful modified variable message, or maybe nothing. Then I do an ugly check of the second output to see if the success message is there. If that's the case, we print it and we are done. So now it's basically ready. I add some more debugging output to see what's going on, add arguments to supply a random seed, and then we can compile it. Because we want to use forkpty, we have to also link the utils library. Here you can see how many executions we get per second per process. This machine has only one CPU, so this will take a while. Let's come back later. Let's see, nothing happened yet. Maybe let's rent a bigger server for a few hours with more CPU cores. Maybe this one. Oh, what? Only 9 executions per second? What kind of crap is that? If you look at the processes, you can see something called Apport. Apport is a system which intercepts crashes right when they happen the first time, gathers potential useful information about the crash and the OS environment. So because we constantly crash a process, this thing is gathering information and slowing everything down. Let's disable the service. To run it, I do some ghetto parallelization. And then let's wait it for a bit. Oh yeah, see, one process output the modify variable message. How amazing is that? I admit, not the most reliable exploit, but it worked. So I'm happy. If you have a better exploit strategy for this year, please share it with us. I'm really curious what other techniques could be used to exploit this program in a more reliable way. Thanks guys, see you next time.